assistant professor. Here he got his undergraduate degree from Harvard, and then he went on to Princeton, where he got his master's degree and also his PhD. And his PhD was in 2020 on topological structures in supersymmetric gauge theories under the advisor of Silvio Bufu. And he is actually an expert in theoretical quantum physics and theoretical high energy physics, applications of quantum information to fundamental physics, and applications of fundamental physics to quantum science and technology. And so he has got a very broad spectrum that combines all the quantum work, also with some cosmology, gravitational work. He's an expert on supersymmetry and Wilson loops and all the advanced topics over there. So we are looking forward very much to his talk, and he's going to talk to us about the universe as a quantum computer. And welcome.
Thank you. Oh, thanks for having me, first of all. Actually, I had no idea that you would be giving such a formal introduction. And in particular, I didn't actually tell you any of that information. So like, yeah, I'm pretty impressed by that. So, but anyway, I am very happy to be here. And also, I've been meaning to visit more often, both because we're neighbors and also because I think we have a lot of interests in common and there could be a lot of opportunity for collaboration. So I've only managed to make it once so far, but I'm happy to have any excuse to come here. And I hope some of you also visit us in Idaho as well. So, when trying to decide what to tell you about today, I faced a choice. I could either talk about something practical or I could talk about something fun, as in fundamental. And, naturally I chose to talk about something fun. So I know it'll be fun for me, and I hope it'll be fun for you too. So I wanted to start off with some very broad motivation for why I like to do what I do. And one thing I like about working on topics related to quantum information science is that it really lies at the intersection of many different fields of physics. And there's a large potential for making impact in all these different fields, right? So on one hand, of course, the principles of quantum information underlie a lot of the quantum technologies that have seen a lot of rapid development. But on the other hand, there are many different points of view from which people like to approach physics, right? On one hand, you might be interested in emergent phenomena or collective behaviors of many particle systems. On the other hand, you might be interested in the fundamental laws that govern things like elementary particles. And quantum information science really has something to say about all these fields. And I don't think that's an accident. I think there's something very deep going on here. And that's the thing that originally attracted me to this field. And I think it's not surprising that quantum information would really blur the line between pure and applied research if you take a sort of operational point of view that our understanding of quantum mechanics is measured by what we can do with it. But today I want to make an even bolder claim, which is the following. I want to claim that the principles used to design quantum computers directly underlie how the universe works, so that by understanding more about one, you can learn more about the other. And one nice example of how this works is actually the field of quantum error correction, which is the study of how to protect quantum computers from noise coming from the environment. And the basic idea here is that usually physical errors act locally. So if you have a bunch of individual quantum degrees of freedom, usually physical errors will tend to corrupt only one at a time. So what we do is if we want to have some information like in a memory or that we want to manipulate somehow, the right way to do that is to store it non-locally in some pattern of entanglement between these individual degrees of freedom. And if you manage to do that correctly, then these local errors, which tend to corrupt local degrees of freedom, will not actually corrupt the information that you store via entanglement. And this is a really powerful idea, right, which people have come up with for engineering purposes. So it's powerful in practice, but it turns out that nature also uses this idea. So it's not just something that the engineers came up with. It's something that seems to suggest that in some sense, nature even thinks like an engineer. So I'd like to illustrate this example in two ways. So on one hand, if we think about the link between emergent phenomena and quantum information, there's this nice fact that actually new quantum error-correcting codes correspond to new phases of matter. And this connection actually goes both ways. So you can discover new quantum error-correcting codes by thinking about phases of matter and vice versa. So one of the prototypical examples of this is Kitaev's toric code, which is actually an example of, well, you can think of it in a few ways. It's an example of what's called a lattice gauge theory. It's also an example of what condensed matter physicists might call topological order. And it's a precursor to the kinds of quantum error correction schemes that are actually used nowadays in quantum architectures like the surface code. And I won't go into much detail about this, but broadly speaking, the kinds of tools that people use when exploring these kinds of connections have a discrete flavor. So they typically think about lattice models, statistical mechanics, and topology, which is a kind of math that's only sensitive to the global properties of some physical system that you're interested in. Okay, but on the other hand, if you think about the connection between fundamental physics and quantum information, there's something to say here too, because it turns out that fundamental physics also suggests new paradigms for quantum error correction and the theory of fault-tolerant quantum computation. So fault tolerance means being able to do computations even when the operations you perform have noise, are imperfect, right? And from this point of view, the tools often have a continuous nature. So they're more familiar to what a high energy physicist would use. And this is my own background. So you might think about things like quantum field theory in the continuum, continuous Lie groups, and geometry, which is a kind of mathematics that's sensitive to local information and not just to global information about a physical system. So let me be more concrete, right? So these kinds of techniques are useful, for example, if you want to think about quantum information processing with quantum systems whose configuration spaces are more exotic. So they might have non-abelian, continuous non-abelian group symmetries. So for example, you might think about storing information in the orientational states of a molecule. That's one example. You might try to do quantum computing with higher level systems like nuclear spins. And these are all contexts in which tools like Lie groups and representation theory play a big role and are really useful. And this is something that I've thought about for the past few years, but it's actually not what I want to tell you about today. Because as I said, I don't want to tell you about something practical. I want to tell you about something really, really fun. So today I actually want to be more ambitious. And the goal for today is actually to go in the opposite direction and to ask, well, okay, look, naturally, it's natural to expect that fundamental physics would have something to tell us about the practical side of quantum information. But can we go in reverse and actually reverse engineer this whole process and say, use the principles of quantum information to tell us something about the fundamental laws of nature at the deepest possible level? So that's really what I want to do. And I want to start by asking this really broad question, right? So by reverse engineering this whole process, I mean taking seriously the idea in the title of this talk that the universe might be a quantum computer. And to do this, you might start out by asking a question like, what are the ultimate physical limits on computation in our universe? And this is a question that doesn't originate with me. I mean, it's been asked by many authors in the past, like Scott Aronson. And the point of view here is that actually, it's great. And the whole idea behind quantum computers is that it's great to use this weird kind of physics to try to build devices that are more powerful than what we have right now. But there's an alternative point of view you could take, which is that merely being able to surmount the challenge of building these devices might actually tell us something deep about the way physics works. And that along the way to building these devices, we might have to overcome certain challenges which would lead to a conceptual revolution of the same magnitude that we saw in the early 20th century. Now, on the topic of those conceptual revolutions, actually, you have to remember that there were two conceptual revolutions in physics that happened in the 20th century, and quantum mechanics was only one of them. The other one was relativity. So one natural question you might ask is, why don't people talk about relativity computers in addition to quantum computers? I mean, it's the same idea. You're just using some weird kind of physics to build a more powerful computer, right? And here I have a cartoon. So let me explain the cartoon. This is meant to evoke something like the twin paradox, right? So here's a cartoon for how a relativity computer might work. So you remember the twin paradox, right? Where, you have a twin, you go off in a rocket ship close to the speed of light. The difference here is that instead of leaving your twin behind on Earth, you just leave a computer, an ordinary computer, running some very long and difficult calculation, which might take longer than your lifetime, right? But naturally, you can't wait that long. You want to see the result. So what you do is you leave this computer here, you board some rocket ship, you fly back and forth, close to the speed of light. And by the time you get back, using the magic of time dilation, well, everyone you once knew will have died, unfortunately. But assuming that your computer had been running the whole time, when you get back, you could just read off the answer, right? This is actually a way that you could use relativity to enhance computers, right? So you agree that it makes sense to consider the notion of a relativity computer. Now, the unfortunate thing is you can do very simple resource estimates for this kind of computer, and you could actually, you could say that the kinds of fuel requirements in your rocket would actually tend to make the scheme impractical, right? But it doesn't actually prevent you from thinking about this kind of thing. But let's actually take it a step further. Why not combine these two things and talk about a relativistic quantum computer? Like, would this actually give you any more computational power? And I can rephrase this as follows, right? So we're asking a sequence of questions. On one hand, what is the computational power of quantum mechanics? On the other hand, what is the computational power of space-time itself? And finally, what happens when you combine those, right, into quantum field theory, which is the framework that combines relativity and quantum mechanics? And this last question, what is the computational power of quantum field theory, is actually not a new question. It's one of the questions that prompted the whole field of topological quantum computation back in the late 90s. And okay, having asked these questions, let me actually just tell you the answer, okay? Here's the answer. So what is the computational power of quantum field theory? Well, I'm sorry if this is a letdown, but it turns out more or less that quantum field theory and quantum mechanics are equivalent in computational power. This was, again, something that people figured out sort of in the early days of topological quantum computation, where essentially they realized that you can use a very special kind of quantum field theory known as the topological quantum field theory to do all the things that any universal quantum computer would be expected to do. So in some sense, and moreover, that you can go in reverse, that you can simulate topological field theories using quantum computers. And what this shows specifically is that, in fact, the topological quantum computing model is equivalent to the circuit model, the ordinary circuit model of quantum computation. Moreover, you can even go beyond this and show how quantum computers can be used to simulate more or less arbitrary quantum field theories, not only topological ones. So this is sort of a precise sense in which the power of quantum field theory and quantum mechanics are more or less equivalent. But I also want to give you some intuition for this statement. So why does adding special relativity into the mix not really give you extra power? Well, I mean, I would think of it roughly like this. The intuition is that, in some sense, special relativity places restrictions on your capability to process information, right? It says there's some upper speed limit, the speed of light, on how fast information can travel, right? So from that point of view, maybe it's not surprising that adding relativity into the mix won't actually give you extra capabilities. But the thing I really want to get to, the really interesting thing, which I have not yet mentioned, is that I've only mentioned special relativity so far. And gravity, or general relativity, is actually a completely different beast, and it changes the answer to this question entirely. So that's what I want to actually get to. So let's actually be even more ambitious and ask, what is the computational power of the entire universe? And to really answer this question, you have to know when gravity and quantum mechanics come together, because naturally you have to consider both if you're considering the entire universe. And another way you could phrase this question is, when are things both large and small? Like when are quantum and gravitational effects significant at the same time? This seems like a somewhat paradoxical question, right? So I'm not suggesting that you should do something like calculate gravitational corrections to the spectrum of the hydrogen atom. That'd probably be a waste of time. But there are certain situations in which it's unavoidable to use both gravity and quantum mechanics. And the ones that I'm aware of are ones involving certain singularities. And those would be when you're talking about either black holes or cosmology. So in the context of black holes, of course, it's natural to combine both, because in some sense, in some very precise sense, black holes are precisely objects that are both large and small at the same time. They're so small that the matter that they formed from has collapsed into something like a singularity, and yet they're large in the sense that they exert a significant gravitational force. So they actually fit the bill precisely. But another context in which it's kind of unavoidable to use both these subjects is when you're talking about cosmology, and when you sort of rewind the clock back to the beginning of the universe. Because at that time, in some sense, the entire universe was small, right? We're used to applying gravity to the entire universe, but at an early time in the history of the universe, when the entire universe was small, you also can't avoid applying quantum mechanics. These are the two situations I'm aware of in which it's actually necessary to use both gravity and quantum mechanics. And what's interesting is that both of these situations are they're almost the same situation, because they're actually characterized by the existence of horizons, which you can think of as some surface that sort of hides something from you, prevents you from knowing something, right? So in the case of a black hole, you're used to thinking of yourself as an observer from outside, where you can't perceive anything that has fallen behind the event horizon. But something similar happens in cosmology, where you can't actually see beyond the cosmological horizon of an expanding universe in pretty much the same way that you can't see behind the black hole horizon. And in fact, this perspective, this cosmological perspective, is more or less what I expect the inside of a black hole to look like. So if you had fallen inside a black hole, it would look more or less like what you see on the right. So in some sense, these two situations are the same situation. And at this point, we can actually go into more detail about why gravity is different. So what makes gravity actually so different from the other fundamental forces of nature? And I would put it like this. Gravity actually violates one of the principles of reductionism that we're used to when doing physics at all. So, for example, when doing particle physics, we often want to explain things like, well, we want to explain particle interactions. So one example is nuclear beta decay, right? So in the early days, people might have written down some effective theory involving 4 fermions just interacting at a single point for explaining a process like this, like nuclear beta decay. So this would be a 4 fermion theory of the weak interactions. But what we learned over time is that if you sort of take a magnifying glass, which really means if you just collide particles at higher energies, you can resolve this kind of process. And you'll find that secretly, this single vertex is actually mediated by a new particle, which we now know as a doubly boson. Right, so this is the whole point of building particle accelerators, and it's more or less the approach that we're used to taking when doing physics. It's the idea that by going to higher energies, we can probe smaller length scales. So this isn't surprising at all, because this is what particle physicists do all the time. What's different is that when you add gravity into the mix, gravity actually imposes some limit on the amount that you can understand what you get out of these particle collisions. Because what happens is that if you collide particles at sufficiently high energies, you'll create a black hole. And if you were to take the approach on the left, where you simply go to higher energies and expect to probe smaller length scales, you'll be disappointed, because what happens is that if you collide more things at higher energies, you create a bigger black hole. And that black hole is like a veil of ignorance that hides whatever was created in your reaction, right? And what this is saying is that actually, when you account for effects of quantum gravity, this whole philosophy that we take when doing particle physics simply doesn't work, because it says that, in fact, if you go to higher energies, in some sense, you produce an object which is associated with larger length scales. The horizon radius of your black hole, of the black hole that's created, becomes bigger, and it hides more and more of the material that's created when you collide these particles. And this is a sense in which gravity is non-local. Some people call it UV-IR mixing. It's some mixing between high energy and low energy degrees of freedom. And it's a very exotic thing, which, you know, most people, when they do quantum field theory or particle physics, are just not used to thinking about. And what this really prompts us to think about is actually the fact that information itself is physical, right? So if we really want to understand how to get past this barrier and understand quantum gravity, what we should really understand is, what is a black hole hiding, right? Because this is the obstacle that we've encountered. Black holes tend to hide information, the products of these reactions at, say, particle accelerators, right? And I think to be more quantitative about that, we can remember that there is this notion of entropy that we have in physics, which you can think of as quantifying our ignorance about the state of a physical system, right? So one of the original definitions of entropy was the number, roughly, well, the logarithm of the number of microstates consistent with a given macrostate. But we learned in the 70s that you can actually precisely calculate what the entropy of a black hole should be. So this is the famous Bekenstein-Hawking formula, which states that in some sense, the entropy of a black hole is given by its area divided by 4 in Planck units. So meaning its area divided by 4 in units of the Planck length squared, which is some very small area. And what does this formula actually mean? Well, it actually says something very profound, not even about black holes, but about space-time itself. And what we can learn from this formula is really the following. So it's possible, and I'm oversimplifying this, but it's possible to do a very simple thought experiment where you think, okay, let me consider a certain region of space and ask, what's the maximum amount of information that that region of space could store? And you might say, okay, well, let's try to cram as much physical content into that little region of space as possible. What the Bekenstein-Hawking formula tells you is that actually there is an upper limit to the storage capacity of a region of space, in the sense that if you were to try to cram more and more stuff into that region of space, eventually it would collapse into a black hole. And if it were to do that, well, then you wouldn't be able to fit any more stuff into that region of space without actually expanding the area of the black hole that it collapsed into, which means the stuff wouldn't actually fit into that region of space with the prescribed area. So in fact, there is an absolute upper limit on the amount of information that a given region of space can store, and is given precisely by the area of a black hole that would occupy that region of space. And this is what we call the Bekenstein bound. So in other words, it says that the maximum entropy that's storable in a region of space scales subextensively with that region. So it means it scales with the surface area of that region and not with the volume of that region. And again, this is something highly counterintuitive if you're used to ordinary quantum mechanics and quantum field theory, where you would think naturally the number of degrees of freedom that you can fit into a given volume is proportional to the volume, right? How can it be proportional to the area? And gravity is telling you something different. And this sort of thought, which I have to admit is very counterintuitive, led to what's actually known to this very profound realization known as the holographic principle, which sort of suggests that, in fact, one should take this picture as seriously as possible, that in some sense, the actual microscopic degrees of freedom in a theory of quantum gravity are literally stored on the surface of whatever region of space that you're considering. So this is a famous picture due to John Wheeler in the late 80s, where he meant to suggest that actually, if you were to tile the event horizon of a black hole, so some spherical event horizon with tiny tiles of area the Planck length squared, each of those could roughly fit 1 bit of information. And this is roughly how you could think of quantifying the amount of information that can be stored inside this sphere. So this is the idea of the holographic principle, and it's called holographic because the idea is that the actual stuff, the part of the universe that's contained inside the sphere, is like a hologram where all the information about that stuff, that three-dimensional stuff, is actually contained on a two-dimensional surface. So it's projected, it's like the information on the surface is projected into the volume in the same way that you would have a hologram in optics. So to summarize, this is like saying that gravity stores information non-locally, right? And this is kind of taking a step further what I said about what I said in the previous slide about gravity having some kind of non-local nature. Okay, but we can take this still further. So we can take this to essentially its furthest logical conclusion, right? So here's an interesting observation. So I told you that gravity is somehow non-local and stores information non-locally. But that's not the only thing that we know that stores information non-locally. Because if you do quantum mechanics, you'll know that entanglement is also a way of storing information non-locally, not in physical degrees of freedom, which are located at certain positions, but in the correlations between them. And in fact, there is a proposal supported by various threads of evidence, which I can't all give, that quantum entanglement is precisely what builds space-time, and that this is what explains the non-local nature of the way that gravity stores information. So the proposal is that actually space-time itself on which we live is the result of the entanglement between some kinds of fundamental quantum mechanical degrees of freedom, which you can't quite see. And it's a very interesting idea, which, well, in its ultimate instantiation, takes the form of what's known as the ADS-CFT correspondence. So what this says, what this proposes, and again, so the details don't really matter so much, but the idea is that any ordinary quantum system, and I'm going to be very literal in my interpretation of this correspondence, but any ordinary quantum system without gravity, without any notion of gravity, can be described by, and in turn can describe, a theory of quantum mechanics combined with gravity. But the catch is that the ordinary quantum system lives in some number of dimensions, and the theory of quantum gravity that it's supposed to be equivalent to lives in one higher dimension. So the ordinary quantum system is what we call the boundary system, and this higher dimensional system is what we call the bulk system, right? So again, this is just a sort of an extrapolation of the logic of the previous slide, where we essentially said the stuff contained inside a three-dimensional volume is actually in some way encoded on the two-dimensional surface. It turns out there's a far more general and powerful version of the statement, which actually pertains to arbitrary numbers of space-time dimensions. And this is the idea behind the ADS-CFT correspondence. And the way it's supposed to work is that actually this bulk gravitational space-time is supposed to be encoded redundantly into the boundary quantum system, which doesn't involve gravity. right? And more specifically, that gravity actually stores information in the manner of a quantum error correcting code. That is exactly what explains the non-local nature of information storage and processing in quantum gravity. So the claim here, so notice what I've done here, right? I've taken, as I said at the beginning, what I wanted to do was actually to take the principles that people use to engineer or design quantum computers and try to use them to explain the way nature works. And this is, I think, probably one of the best examples of how you might actually try to do that. So just to give you one toy model of how this might work. So again, this is just a toy model, but by now there are many examples of what are called holographic quantum error correcting codes, where the idea is simply, well, let's consider an ordinary quantum mechanical system consisting not of qubits, but of qubits. So each degree of freedom would be a 3-level system. And let's say we take 3 of these qubits and arrange them on a circle. So their total Hilbert space, of course, would be 27-dimensional. There's a certain way of encoding a single logical qubit in a pattern of entanglement between these 3 physical qubits, the details of which I'm omitting. But the point here being that, in fact, it's possible to do this in such a way that if you were to completely erase or destroy one of these qubits on the boundary, you could still recover this encoded qubits worth of information that's encoded in the entanglement between these boundary qubits. And this is supposed to be a model for how ordinary quantum mechanics can actually encode a theory of quantum gravity. There's some way in which if you erase a portion in which actually the bulk gravitational theory is encoded redundantly into the boundary theory in such a way that even if you were to erase a portion of the boundary theory, you'd still be able to recover all of the information or some or most of the information in the bulk.
Why is the boundary of high energy in the bulk?
The boundary of so actually you should think of it like this. The boundary is a circle, but the bulk is a disk. So in this case, actually, the bulk is not a point, it's actually a disk which is bounded by the circle. So that's the kind of cartoon I wanna propose in the bottom here. So it still fits the paradigm of the boundary being 1 dimension less than the bulk. In this case, the bulk is actually the whole disk inside the circle. Yeah. Okay, but I do want to be a little bit more concrete. But before I do that, I kind of want to phrase this in as provocative a way as possible, okay? So modern physics suggests the following. We live in the matrix, okay? But the matrix is a quantum computer. It's not a classical computer, okay? And the illusion of the matrix is maintained by quantum error correction. So it's as if nature itself is performing quantum error correction to uphold the simulation that we're all living in. And again, okay, now to be more concrete, I want to actually take this idea further and say, well, let's use the matrix. Let's use the matrix to do physics. Okay, some people use the matrix to dodge bullets, but you can also use it to learn about physics. So that's what I want to do. And again, we're going to do this by taking seriously the idea of the universe as a quantum computer. Okay, so I want to start with a topic which presumably is of more interest to computer scientists, or apparently is of more interest to computer scientists than to physicists, which is the notion of computational complexity, which just roughly it describes or quantifies the resources that are required to solve a given problem. These could be resources in space or resources in time. And okay, so why should a physicist care about a notion like computational complexity? It's because I want to claim that complexity is actually a fundamental property of physical systems in the same way that entropy is. So, okay, here's an example which condensed matter physicists might be more familiar with. So there's this notion of what's called quantum Hamiltonian complexity, where the idea is that you can sort of quantify the complexity of a given Hamiltonian by asking how hard would it be to prepare the ground state of that Hamiltonian on a quantum computer. So just to give you a simple example, suppose you have a lattice system, so a system of spins on some triangular lattice, okay? And this system of spins has some Hamiltonian. Whether that Hamiltonian is ferromagnetic or anti-ferromagnetic just depends on some overall sign. So whether it's a plus or minus sign in front, whether or not the Hamiltonian wants to make the spins point in the same direction or in opposite directions. Right, so if it's ferromagnetic, the Hamiltonian will want to make the spins point in the same direction, in which case the ground state will just be a product state. All the spins are indeed pointing in the same direction. But if it's anti-ferromagnetic, what happens, of course, well, classically, it'll want to make the spin point in opposite directions, but classically, since the spins are on a triangular lattice, it's not possible for the spins on the three vertices of a triangle to all point in opposite directions. So the system will be frustrated classically, and that has the consequence that the quantum mechanical ground state looks very complicated. So in the case of in the anti-ferromagnetic case, the quantum mechanical ground state might look something like a very complicated superposition of all possible Bell pairs on this lattice. And you take a huge sum over all possible ways you could tile this lattice with Bell pairs so that the entire state is translation invariant. And I don't know about the details, but I think this is something that some people call a spin liquid, something like this. So there's a very intuitive sense in which one of these states is more complicated than the other, right? And you can actually quantify that by asking, well, how hard would it be to prepare such a state on a quantum computer? And it turns out that this notion of complexity, the notion of how hard it is to prepare on a quantum computer, is related to other properties of the state, like the amount of entanglement. Like you could ask, does the entanglement in the ground state obey an area law or volume law or something like this? All these facets are related. And this example is just to illustrate that complexity is actually a useful thing to talk about when characterizing quantum mechanical Hamiltonians. Here's another example from a completely opposite branch of physics, where complexity might enter. And that's when talking about the interiors of black holes. So in light of the ADS-CFT correspondence, well, actually, before getting to that, so it's very heuristically, and again, so I'm not a relativist, so I'm going to be very heuristic here. It's possible to choose a nice system of coordinates or nice time slicing in which you can roughly think of the interior of the black hole as, say, growing at the speed of light. And you can roughly think of this as an explanation for why, if you fall into a black hole, you can't get out. So the image I'm showing here, well, actually, before I get to that, let me say that it had then been conjectured, well, in light of the fact that the interiors inside black holes tend to grow, by the ADS-CFT correspondence, this is supposed to say something about a completely equivalent quantum mechanical system. So the question is, what exactly is that saying about quantum mechanics, the fact that the interiors of black holes actually grow? And it was conjectured some number of years ago that the evolution of the volume of the interior of a black hole actually reflects the growth in the complexity of a quantum many-body system over time. And that this has to be something deeper, more subtle than just the quantum system coming to thermal equilibrium. Because in some sense, a black hole already has a temperature, already radiates, and has in some sense already, well, in some situations can be thought of as having already come to thermal equilibrium. But there's something still growing, even for a black hole in thermal equilibrium. I should say I'm omitting some details here. Like, for example, the picture I've drawn here is actually that of a black hole in anti-de Sitter space, not in the sort of flat space-time that we're used to. And another complication is that this is technically a two-sided black hole with two asymptotic boundaries. So in fact, when you take a given time slice of this black hole, it actually, the spatial geometry actually looks like a wormhole that's growing in time. But so this is not actually a realistic black hole that either exists in our universe or that formed from collapsing matter, but I'm going to ignore those details for now. And this line of thinking about the growth of volumes of black hole interiors actually led to a conjecture for quantum mechanical systems, which had nothing to do with black holes. And that conjecture was that if you have a sufficiently generic quantum system with sufficiently generic Hamiltonian, then under time evolution, its complexity, in the sense of computational complexity, should grow linearly in time for an amount of time that's exponentially long than the size of the system, or the number of degrees of freedom. This conjecture by these authors, Brown and Susskind, was motivated by considerations in black hole physics, but it actually has nothing to do with black holes. It's just a conjecture about the behavior of the dynamics of quantum mechanical systems. What's nice is that this conjecture has actually been proven in some cases for pure states of quantum systems. For example, there are certain toy models for quantum time evolution, like random quantum circuits, in which you can prove statements like this rigorously. But that's not the whole story. And it's not the whole story because actually, despite the fact that this notion of quantum circuit complexity is well developed for closed quantum systems and pure states, in nature, all quantum systems interact with their environment, which means that they're open. Which means that to make a statement that's actually useful, we kind of have to go beyond this neat mathematical setting in which we've proven these precise statements about complexity, growth, and saturation. And that's actually the thing that I wanted to mention at the end, which is that with some collaborators in UT Austin, this is exactly what we did. So what we did is we actually formulated and proved a similar conjecture about how computational complexity grows in quantum systems once you take into account that these are open quantum systems which interact with their environment. Right, so what we did is we extended and proved this conjecture for mixed states, which you can think of as subsystems of a bigger quantum system. And I think this is nice for two reasons. One, it has some fundamental importance in the sense that it gives you a new understanding of how quantum systems equilibrate beyond just coming to thermal equilibrium. So it tells you more about how quantum systems behave over time. But it also has some practical importance in the sense that understanding the behavior, the complexity of these mixed states as a function of time is actually relevant for things like simulating open quantum systems and using open quantum systems to perform universal quantum computation via operations like measurement and dissipation. But what's neat, I think, beyond the actual statement of this fact or this conjecture that we actually proved is how we proved it, because we actually proved it using gravity. So I mean, I think that's the really cool thing. It's not even the statement itself, but the fact that we actually proved these facts about, or intuited these facts about quantum mechanical systems by using what appeared to be a completely different branch of physics. So the tool that we actually used, as I kind of alluded to earlier, is this notion of holographic duality, which is another term. Well, it's a more general framework for what people call the ADS-CFT correspondence, which is just the idea that in some contexts, a strongly interacting quantum mechanical system is exactly described by a classical theory of gravity. So in some sense, this is a tool, this is a framework that actually geometrizes quantum mechanics, allows us to turn algebraic problems in quantum mechanics into problems in geometry. And one concrete way in which this works is that, to be a little more quantitative, there are certain properties of quantum systems like entanglement entropy, which you can actually directly draw correspondences to, where you can actually draw a direct correspondence between these quantities and certain geometric objects. So if you think of a boundary system, which describes a quantum mechanical system without gravity, there are certain ways in which you can map properties of that boundary system to properties of geometrical surfaces which live in this bulk higher dimensional gravitational theory. So this is just a single, so these pictures which I'm including here are really just a cartoon of a black hole which lives in 2+1 dimensions. So I've drawn time slices here where each disk is a two-dimensional disk. If you were to include the time direction would kind of go out of the page and turn these into cylinders. The quantum system is what's living on the circular boundary of this disk. And these red curves you should think of as surfaces, or in this case, curves which extend into this higher dimensional gravitational bulk, which end on the endpoints of certain arcs on this boundary circle. And those arcs describe the subsystems on which this quantum mechanical system live. And the claim is that, in fact, the lengths of these red curves directly compute precise quantities associated to this quantum system, like the entanglement entropy of the given subsystem of that quantum system. And you can go further than that and ask about the dynamics or the time evolution of these properties of quantum systems. And it turns out, so the details don't matter, but you can think about how the behavior, how these surfaces in the higher dimensional gravitational theory actually behave over time, and use that to deduce properties of how these quantum mechanical properties would in turn behave over time. And in particular, there are various kinds of minimum area surfaces that you could draw in the bulk higher dimensional spacetime. And some of them have, depending on how your bulk geometry evolves over time, some of these surfaces will exchange dominance in the sense that some of them might have smaller surface area at one time and larger surface area at another. And depending on the precise relation between the areas of these surfaces, you can actually infer non-trivial dynamics in the dual quantum system, like things like how the entanglement entropy grows over time and how the system thermalizes. And the result of the work that we actually did a few months ago is that in fact holography predicts a universal behavior for how complexity behaves in open quantum systems and subsystems of a closed quantum system. And it turns out that complexity, unlike entanglement entropy, which I mentioned on the previous slide, is measured by volumes enclosed by these minimum area surfaces in the bulk spacetime, instead of the areas of these surfaces. And you can deduce some nice results via this holographic way of thinking, which are actually reflected, or you can cross-check them using techniques from the theory of random quantum circuits, which is a sort of toy model for how chaotic quantum many-body systems behave over time. So I just want to briefly flash for you roughly what the result is. And the claim is that for a generic quantum system, there are essentially three regimes for how complexity will behave over time. So the x-axis here shows the fraction of the subsystem of some overall quantum system that you're considering. So remember, we're actually interested in open quantum systems, and any open quantum system can be thought of as a subsystem of some bigger system. This fraction can range from 0 to 1. The y-axis shows the time after which the complexity, in the sense of computational complexity, of a state of this subsystem, it shows the time after which this complexity saturates or stops growing in time. And the idea is that there are three distinct regimes for how complexity behaves in time. If your subsystem is sufficiently small, if your subsystem fraction is sufficiently small, that is a regime in which the complexity essentially saturates instantaneously. There's another regime between some critical fraction less than 1/2 and the fraction 1/2, between which the complexity growth of a quantum mechanical subsystem grows for a time that's short, and it's only polynomially big in the size of your subsystem. And finally, when you consider a subsystem of size greater than half that of your entire system, it turns out that the complexity will grow for an exponentially long time, for a time that's exponential in the size of the subsystem that you're considering. And you can actually, it turns out, derive, in a precise sense, this picture by actually doing calculations involving black holes in anti-de Sitter space. The details of which I won't get into, but this is how we actually derived this behavior in generic quantum systems. And what's cool is that there are a few things. One, you can check the transition, this sharp transition between regimes 2 and 3, actually using the theory of random quantum circuits. So you can show this is not science fiction, and we're not actually fooling ourselves by thinking we can actually say something about quantum systems just by doing gravity. What we did here is that we actually inferred some properties of quantum systems which we would have had no idea even existed if we did not have this hint from some higher dimensional gravitational theory. Once we had that hint, we were able to actually prove them using rigorous methods, using quantum information theory alone. And what's even cooler is that we can actually go beyond, using this gravitational picture, we can go beyond these quantum techniques, and we can actually conjecture properties for generic quantum systems which are not accessible via traditional techniques in quantum information theory. And some of those include the transition between regimes 1 and 2, which actually only happens at finite temperature. And this is a regime which is actually completely out of reach to standard techniques like random quantum circuits. So it's something where the gravitational picture actually gives us some kind of handle on quantum systems that we would not have had otherwise. Okay, so, well, again, the details don't really matter, but just to give you a rough picture of how this actually works from the gravitational point of view without writing down any equations, the point is the following. So remember, there were three regimes, right, in the previous picture. And those three regimes map onto a very specific picture in holography. So in the way that gravity maps to quantum mechanics, where again, you can think of these wormholes, which I've drawn, as the interior of some two-sided black hole. And the idea is that by tuning the size of the subsystem, which is represented here by, well, it's probably hard to see, but there's some green intervals on these two boundary circles. So each wormhole picture, which I've drawn here, is like a cylinder topologically, and the boundary consists of two separate circles. There are certain green intervals on these circles, or on the edges of these cylinders, which indicate the size of the subsystem that we're interested in. And what these pictures show is that depending on the size of your subsystem, and also depending on the length of the wormhole, which grows with time, you can actually deduce how the complexity, in the sense of computational complexity, of that quantum mechanical subsystem behaves with time by looking at how the lengths of certain surfaces actually grow in this higher dimensional bulk spacetime. So I've indicated these surfaces with with colors like red or blue. The details, again, don't really matter. But what's most interesting, I think, is the fact that in this regime, going between regimes 2 and 3, we have sort of a sharp transition or topology change in which all of a sudden the volume enclosed by one of these surfaces actually includes the entire wormhole. And this is actually what explains geometrically why there's a sharp transition between regimes 2 and 3, where in regime 2, the complexity grows and saturates after a very short time, whereas in regime 3, the complexity actually grows for an exponentially long time. So this is a geometrization of what happens in quantum mechanics. So again, the details don't really matter, and because they don't really matter, I just actually want to give you a qualitative summary of the main lessons here. And I would put it like this, right? So if you know how to ask the right questions, gravity can provide universal predictions for properties of strongly interacting quantum many-body systems, such as their entanglement entropy, their complexity, and how these things evolve in time. And this is a very useful point of view because actually holographic duality is a strong, weak duality, which means the more strongly interacting the quantum system is, the less strongly interacting the gravitational system is, and therefore the easier it is to do calculations on the gravitational side. And in this way, the second point is that gravity can provide a shortcut to difficult calculations in quantum many-body physics or quantum information. But I think the most important point is that gravity is in some sense an oracle, which can tell you things about seemingly unrelated areas of physics, and that there's a lot more to learn from gravity if you just ask the right questions. And what it seems to illustrate is that actually there are certain areas of physics, like gravity and quantum mechanics, which initially might not seem to have anything to do with each other, but might secretly be the same thing. Okay, so that's what I wanted to tell you today. Thank you.
Okay, thank you very much for these fascinating thoughts. Time for questions. Lucas.
Yeah, something you've mentioned toward the end. So you use ADS-CFT correspondence as something, gravity is a convenient tool to work out how the quantum convexity works, right, as a function of time.
Yeah.
But then if I heard you right, you also said that you also did a calculation just using quantum information theory.
That's right.
Opposed to gravity.
That's right.
Because the gravity part appears like magic. It doesn't have
That's
to
right.
do with any deep insight.
That's right.
But did you gain any insight by doing a self-contained calculation within quantum information?
Well, yeah, we can, the thing is, we gain different insights. So we gain complementary insights. So there are limitations. Well, okay, without getting into too many details, there are limitations to what you can do via random quantum circuits. So first of all, random quantum circuits are only, so those are the precise tools that we used on the quantum information side. And they're limited in the sense that they're only a toy model for how quantum systems actually behave over time, because they're not associated to time evolution under a fixed Hamiltonian. It's more like you apply a random sequence of quantum gates and ask, and hope that it reflects the behavior of a sufficiently generic quantum system evolving under a time-independent Hamiltonian. Using random quantum circuit techniques, generally, we can only place bounds on how the complexity behaves in time, so upper and lower bounds. In fact, we can't be quite as precise. We can't make statements which are quite as precise as what we could get from gravity, but we can at least do sanity checks that what gravity is telling us is consistent with what we would expect on the quantum information side. I would say that we actually, my point of view is we actually get more insight by doing the gravitational calculation than by doing the quantum calculation. Because first of all, without doing the gravitational calculation, we wouldn't have known which quantum calculation to do, like what to even look for in the first place. And second, gravity doesn't just give us bounds on how complexity behaves. It actually tells us literally how complexity behaves with time. And not just complexity, but other properties like entanglement entropy. But complexity is the new part that I wanted to tell you about. Yeah.
Right.
Yeah, Jim, question. Maybe I don't really get certain things.
Yeah.
Are you saying your regime 3, and maybe I don't understand exponentially long time, but are you saying that because of this gravitational analogy, people have been able to discover how entropy increases in a general isolated classic quantum system?
That is actually exactly what I want to say.
And that seems like a huge event.
Yeah, I think it's amazing. If you think it's amazing, then I agree.
But also, this is the equilibration.
Yes.
The internal equilibration of a closed system. is now been deduced from this, is what you're saying?
Yes, yes, although I should say, okay.
The general system.
Yes, for a general system, but there are some caveats because, you know, I haven't phrased this as a precise mathematical statement. So like in physics, we generally don't prove things to the same level of rigor as mathematicians. And the thing is, the issue with physicists, which mathematicians will complain about, is that we don't define things precisely. So that's actually the issue here. So there's a conjecture, but what do we mean by a general quantum system? That's kind of open to debate. So the thing is, I think there's some very deep facts, some very deep connection between quantum mechanics and gravity, but I haven't actually given you a very precise statement. Like I haven't told you what it means to have a sufficiently generic quantum system and what are the precise regimes in which this kind of connection holds. Where might it break down, right? Like if you have a totally non-generic quantum system, there's no reason to expect complexity or entropy to behave in this way. It's only like for systems which you might call sufficiently chaotic that you would expect things to behave in this way. Yeah.
A follow-up to that.
Yeah.
How accessible is the understanding of theory that's needed to go and work in gravitational analogy to analyze the systems? What background is one?
Well, frankly, I think from some point of view, it is actually very accessible because, you know, as I mentioned, holographic duality is a strong weak duality. And what it means is that the harder the calculations are on the quantum mechanics side, the easier they are on the gravitational side. And that's a big advantage to this way of thinking. So in some sense, you don't, in fact, look, I'm not a relativist, but I did a lot of these gravity calculations. Okay, like if it's easy enough for me to do, I think there's something worth doing there. You don't need a huge amount of background to actually leverage these tools. Now to actually, okay, but then there's a different question you can ask, like how do you actually discover these tools? How do you probe the landscape of validity of these tools? That often requires string theory. So that's kind of something separate. Like if you treat these tools as a black box, no, not much is required. But to actually understand precisely the regimes in which these tools work and to discover new such tools often does require a lot of math. Yeah.
Yeah, so you were talking about like different subsystem fractions.
Yeah.
What is like the correspondence on the gravity side to like different fractions? Like how would you go from open quantum system to closed quantum system?
Yeah, absolutely. So here I'm imagining, so first of all, so any open quantum system can be thought of as a subsystem of a closed quantum system, and that's all I'm using. So you're right. So if I go back to this picture, yeah, the bottom axis indeed shows you the subsystem fraction, and then if we go to the picture in geometry or in gravity, so I didn't spend much time on this, so maybe it's actually might be hard to interpret these pictures, but the subsystem fraction is given by the lengths of the green intervals on the boundary. And I realize it might be very hard to see these green intervals, but if you stare at it, you might see there are actually green lines in each of these wormholes which cover a portion of the boundary circle. And those green intervals represent the subsystem, whereas the entire black circle represents the entire system. So what you tune when you go along this x-axis is the length of these green intervals, which are identical on either side. I've chosen identical intervals on either side for reasons which are not really important.
The length of these intervals show up when you're doing the gravity, the computation?
Yeah. So in particular, the ratio of the green lengths to the circumference of the circle, that's precisely what I'm plotting on the bottom axis here. That's the subsystem fraction. It's just the ratio of the lengths of the green intervals to the entire circumference of the circle. That's all.
Yeah, just to follow up, is the universe a closed system or an open computation?
You know what? That's a great look. I'm not sure why you would expect me to know the answer, but I don't know the answer. But the thing is, there's actually a huge amount to say about this. Look, I'm not an expert on this, but the thing is, there's this very counterintuitive fact that if the universe, so there are arguments coming from various angles in string theory and quantum gravity that if the universe were actually closed, its Hilbert space would be one-dimensional. Okay, that seems very counterintuitive because how can a one-dimensional Hilbert space explain the complexity of physics that we see in our universe? And there's got to be something about the notion of being an observer in our universe and of actually considering a subsystem of a closed system that accounts for all the complexity that we actually see in everyday life. I don't actually know how that works, but there are very strong theoretical arguments from quantum gravity that if the universe were indeed a closed system with no boundary, just closed, that in fact its entire Hilbert space would be one-dimensional, in which case quantum mechanics at the scale of the entire universe would be trivial. But then there remains a puzzle. How does that explain the fact that quantum mechanics seems non-trivial to observers like ourselves? I don't know. And moreover, I don't even know if the universe is closed. I'm just saying, if it were closed, people think this is what would happen. I don't actually know.
Wait, there was an online question about SYK or something.
Yeah, Steve had a question.
Sure.
Maybe you can formulate it.
He hasn't specified it.
Okay.
Steve, do you want to ask your question?
What was it?
I was having trouble with my mic.
Well, okay. I heard the words SYK. So
Yeah. So are you using something like SYK to define what a quantum chaotic many-body system is, or are you thinking something different?
first of all, okay. First of all, I never defined quantum chaos, and I think I'd be the one asking you that question. Like I don't think you should be asking me what the definition of quantum chaos is. Whatever. This goes back to an earlier question. Like I haven't actually precisely defined some of the terms that I'm using, but I'm actually not working in the context of a specific chaotic system like the SYK model. This is something that's first of all supposed to be much more generic and hold for any chaotic quantum system, whatever chaotic means, and it's also supposed to hold in arbitrary numbers of dimensions. It's not just a correspondence between, say, a two-dimensional theory of gravity and a one-dimensional theory like the SYK model. It's supposed to be more general than that.
But you use the term strongly interacting many-body system or something like that.
Right.
But are you assuming that you just have one and two body interactions, or what goes into that?
That is a question which I've deliberately not answered because it's a question which, at the level of detail that I'm working, I don't think I'm capable of answering. I mean, there are general, okay. Short answer is I don't know whether it suffices just to consider two-body interactions. I don't think I'm capable of answering that question right now. Because again, I haven't clarified exactly what it means to be generic or chaotic. And I think actually specifying that precisely is a very difficult question. It's very much an open question. Like, what exactly does that adjective mean? And to precisely which quantum systems does holographic reasoning apply? I haven't tried to answer that question.
All right.
Okay, thanks.
We have a lot of grounds for good collaborations in the future.